Now you've seen an expression for how the length changes as we heat an object. What we're going to do now is derive an expression for how the volume changes as we heat an object. As you know from high school or possibly primary school, the volume of a rectangular prism is given by the length times the width times the height. So the final volume as we heat this rectangular prism is going to be given by the initial volume plus the change in volume. So this term here shows the final volume, and the final volume is equal to the final length, the length plus the change in length, times the final width, the width plus the change in width, times the final height, the height plus the change in height. Okay, so the change in length is given by alpha times the initial length times the change in temperature. Same thing for the change in width, but with a W, and same thing for the H, but with an H instead of the L. Now, each of these, we can pull L out as a common factor here, W out as a common factor here, and H out as a common factor here. So we'll have L, W, H. And then when we pull those out, we've got 1 plus alpha delta T left for each of these cases. So there's 3 of those, so that's cubed. So we've got length, width, height, 1 plus alpha delta T cubed. And so now we want to expand this. To expand this, we can use Pascal's triangle, which tells us that the coefficients out the front are 1, 3, 3, 1. So we've got 1 plus 3 alpha delta T plus 3 alpha delta T squared plus alpha delta T cubed. Now, this was only a linear approximation, so it's wrong to include squared terms and cubic terms. As it was a linear approximation, that meant that previously we were ignoring squared terms. So it would be actually incorrect to start including squared terms now, because there would be other terms that we're not including, which are of an equivalent magnitude. Length times width times height is just the initial volume, and we ignore these because it's incorrect to include them. Also, alpha delta T is a small number, much less than 1. So alpha delta T squared is even smaller. Alpha delta T cubed is very, very small, so we ignore these. So we've got, this is the initial volume times 1 plus 3 alpha delta T. So the initial volume plus the change of volume is equal to the initial volume plus 3 alpha delta T. And so the change in volume we can write this way, which is just equal to 3 alpha delta T times the initial volume. Now, for metals, we generally present alpha as a linear expansion coefficient because it makes sense to think about a meter of a material. And so if we're given a linear expansion coefficient, we can work out how the volume changes using this formula here. However, for something such as liquids, it doesn't make sense to have a linear expansion coefficient because what would a meter of water look like? It's not really a very good concept. So instead we have a volume expansion coefficient, beta. So 3 alpha is equal to beta. And what you're given really depends on whether something's a solid or a liquid, but you can convert between these two. Something for you to try is show that for a rectangular plate, the change in area is equal to 2 times alpha times the initial area times the change in temperature. A is the surface area in this case.